We are used to thinking of quantum computing as the domain of supercooled dilution refrigerators and laser pulses. But what happens when you force the fluid, multi-state probability of a quantum system into the rigid, physical holes of a 1950s paper punch card? This manuscript attempts that exact transition. It takes classical computing terminology, like data nibbles, and applies it to recording quantum superpositions. Traditional computers record absolute states, like these linear strings of ones and zeros at the bottom of the page. But a quantum state exists as a probability between those absolutes, and you cannot accurately record a fluid probability using a fixed binary hole punch. To bridge that gap, the author developed a completely bespoke mathematical syntax termed Qxbin, or O-binary. We are going to rigorously decode the logic of the syntax, because mapping this math is the only way to understand the physical prototype proposed at the end of the text. If the internal equations hold up, what we are looking at is a complete theoretical schematic for a localized analog quantum simulator. The text establishes a baseline. This top section, labeled binary chain, maps out a classical bit array. These circles correspond to ones and zeros, serving as the control group. Immediately below that, the concept shifts. The author introduces the quantum chain. The geometry of these new nodes is specific. Instead of a single point in a sequence, we now have a central coordinate surrounded by 4 peripheral state indicators. This physical layout signifies a jump from a flat sequential data line to a localized cluster capable of holding multiple values simultaneously. This introduces an immediate mechanical problem. You cannot map standard binary ones and zeros onto a 5-point cluster without losing the relational data between those points. Because the physical structure of the data has abandoned flat lines for clusters, the author is forced to invent O-binary to handle the multi-point logic. This is the specific mathematical formulation created to govern those nodes. The system abandons flat absolute integers for a relational fraction written as I over O. The text defines the superscript n as I over O and the subscript m as 0 over 1. The author then applies positive and negative degrees of power to these relational variables. When we substitute those defined values back into the base equation, the n and m swap out, leaving us with a complex stacked fraction, essentially a fraction to the power of another fraction. This resulting stacked fraction is the mathematical representation of a probabilistic superposition. A fraction is inherently unresolved. By defining the state as a ratio, the formula captures a fluid probability that has not yet collapsed into a definite integer. This unique fractional notation allows that probability to be recorded as a discrete coordinate within a matrix. The superposition is no longer a theoretical abstraction. The math successfully locks the probability in place. O-binary notation acts as an engineering bridge, a tool to force quantum probabilities to behave nicely within rigid classical matrices. From single isolated equations, the manuscript begins compiling those fractional states into dense mathematical blocks. The individual n1 and n2 variables are merged to create a larger unified state. Single quantum probabilities stack to build a complex multivariable array. The author defines this resulting complex array as a representation of spheric data. Unlike a linear stream of classical bits, spheric data operates as a multidimensional, continuous stream of probabilities. The matrix architecture serves as a rigid container, designed to trap and hold this continuous data so it can be read. These complex state matrices form the functional logic gates of the Qxbin system. The theoretical math is now ready to be mapped onto a physical storage medium. This hand-drawn grid represents the physical architecture proposed to house those dense matrices. The 2x2 mathematical matrices from the previous scene map directly onto the 4 quadrants of this visual grid. This layout connects back to the classical data sizing mentioned earlier. The text specifically refers to a coordinated I/O state organized into nibbles. Using nibbles allows the author to organize complex quantum probabilities into manageable, classical-sized clusters on the grid. The goal is to achieve punch card format simplicity for reading quantum data. A scanner passing over this grid treats diffractional matrices as physical bumps or holes on a surface, translating the complex geometry into a readable data stream. Mapping multi-dimensional quantum states onto a flat 2D physical plane allows for extreme computational density. This mapping process takes abstract O-binary math and makes it physically recordable on a medium. The grid serves as the functional blueprint for the physical storage prototype, anchoring theoretical math into the hardware schematic, driving the final conclusion. The manuscript concludes by detailing the specific physical hardware proposed to bring this framework to life. The author proposes an unconventional medium, using magnetized paper to act as the analog punch card, utilizing components simulated from magnetic keyboards. Reading these cards would require the use of Hall effect simulation. A Hall effect sensor measures magnetic fields. As it passes over the nodes on the magnetized paper, it registers the multi-state matrices as physical magnetic variations, effectively reading the unresolved superpositions. The final objective of this entire architecture is the creation of a localized, personal qubit simulation processing system. The author closes with the analogy of building an airplane to a horse, a final attempt to force classical binary systematics to carry the weight of quantum computation. While purely theoretical, the manuscript's logic is internally consistent. It stands as a complete, end-to-end blueprint for bridging two eras of computing through custom mathematical syntax and analog hardware.